Okay, this is lecture 37 on invariant maximality by Harvey Friedman. Please.
Thank you. Well, it's no longer invariant maximality. The title of the book and the field has been changed unilaterally without a vote to embedded maximality. So here's what's happened. The way I was doing things with multidimensional invariance, I thought was going to be better, more convincingly mathematical than the 2025 version, which emphasized one-dimensional partial maps. I changed my mind about this because of the inability to take the naturalness far enough. So there are two ways to cast this very mathematically, this whole subject. One is to go after the simplest possible notion of invariance that leads to incompleteness of a maximal chain. And that has been my idea from the beginning. And the other idea is to back up from that slightly and talk about one-dimensional embeddings. One of the ways I was doing invariance is really just the same as the notion of embedding, is to do one-dimensional embeddings and have some extremely enticing sufficient condition for the embedding to work. Then backing off and saying, oh, here are some simple examples of things that meet that condition. Another thing, and this is greatly preferred by me now, this approach, particularly because of the fact that we have an old development, a pretty complicated one that hasn't been changed, it's still here, that all of the finite embeddings have been completely classified. What finite functions can you use has been completely worked out for some time without change. So we have a setup where we ask for a maximal chain. We look for a maximal chain that's embedded by a particular function. If the function is finite, we understand exactly when you can do this and when you can't. That complete information has been around for quite a while here. Then what happens with the infinite embeddings? And the point is then that we look at what's called the almost identities, which is a very simple kind of infinite map. An almost identity is an identity function union of finite function. In other words, it's almost the identity. And the whole of embedded maximality theory is now simply within that context. There are very simple little examples of almost identities for which it's independent whether or not you need large cardinals to prove that they're usable. Usable means every invariant relation has a maximal chain that's embedded by the function. This is a very good situation. I do have a very simple maps that you have to use large cardinals to prove they're usable, but even more convincing, there's a general theory where I understand sufficient conditions. there are open problems connected with getting necessary and sufficient. Necessary and sufficient is probably within human capability, but not this human yet. So that's a very intriguing open setup. All right, now this lecture won't be super polished, and there's some formatting missing and so forth, because I had to spend a lot of time thinking about how do I actually say this and set this up. I decided that there should be one theorem called the almost embedding usability theorem, just one theorem. It has some corollaries, which are nice, but there's just this one theorem with this one pithy name. This is also an improvement. I've learned, as many people have, that sometimes less is more, especially if that more is hidden away from the main event, but immediately accessible for those people who want to know it or want PhD theses topics and so forth. So it took a long time to get here, but I think this is it. In other words, I straighten out this chapter, which is not fully done yet, and there's a crucial thing that has to be checked, but it looks very good. And so this should be largely wrapped up next week. Maybe one more, maybe next week, maybe a week after something gets complicated, where I want to add something. And so we have the unchanged, never changed reversal that's already been done, as you know, and we link to it nicely as before. And so this chapter 3 is what we're talking about. This chapter 3 is has some of the style of our chapter 2 that we were doing with invariant maximality, but also incorporates quite a bit from the old chapter 2, from the old chapter 3 from 2025. So the only thing that is totally unchanged is the introduction is totally unchanged from the empty set, which it still is for obvious reasons. And this chapter totally unchanged. This was just started but it has to be revisited with great care. Revisited. This hasn't been started. This is the old core mathematics stuff. The language has to be changed. The emphasis has to be changed. The content probably not much changed to incorporate the fact that we're talking about embeddings only. So, so the book starts off with embeddings with no maximality. Embeddings with no maximality in the context of core mathematics, piecewise linear and so forth. I do it on the reals. There'll be comments about you can also do it on the rationals because the rational is a perfectly good ordered field. So, you know, this is but it's nice to do it on the reals. I don't think that there's any difference between the reals and too much difference, excuse me. I shouldn't say no difference between the reals and the rationals in the core mathematical part. And then this is what we're talking about, which has been gone through major agonizing revisions. This has been constant and don't expect it to change. There is something clearly I'm going to not do in this book. a more involved reversal connected with refuting, connected with addressing. All right, I'll come to it. I have a conjecture about this stuff in three that you'll see, but I don't really want to get into it this book, I think. All right, and then this has to be rethought, although it started. All right, so there we are. So now this is the chapter 3 we're doing. It's now called Embedded Maximality. This hasn't been written, for obvious reasons. This is totally unchanged, except a couple of definitions, terminology has been changed. This is totally unchanged, is preparation. What happens when you don't have the embeddings? You just want to talk about maximality. Instead of Q, you will always see -1 closed. Oh yeah, that's the other thing. No more Q. It's always -1 closed. So we don't have to make this apologetic move that I was making before. Another reason why I moved to this. I used to do this stuff on Q, which I thought was a big improvement, but to get incompleteness, I had to bring in intervals or restrict things to intervals with the endpoints. Now everything is just this one interval. This was a good idea I had in 2025. I thought it was going to be improved on, and this is not improved on. This is a very good idea for the way I do it now. Okay. Then we really get going with embedded maximality and usability. We start with the most basic usability. Usability of a one-dimensional function is what we're talking about. One usability means it works in dimension 1, and this turned out to be trivial and it's handled there. There's some general nonsense about how good usability, the notion of usability is, like it's closed under inverse. If F is usable, F inversely, that kind of thing. Composition, various things like this. Then we have the two fundamental necessary conditions. This has been around forever. This is unchanged. So is this. This has been unchanged. This is a simple triviality. It used to be called dimension reduction. Now it's this. Obviously, you want this. All right. Now, this part, section 3.5, has been totally unchanged from the previous. Totally unchanged. And gives a complete description of what finite functions can be used in embedded maximality, what finite functions. And all of this stuff is done in CIFA, some of it in EFA. CIFA is super exponential function arithmetic. All right, so there's nothing really new here. Okay, so now we get into the real new stuff, which caused me to move back into this, move into embeddings exclusively now. I mean, somebody can write I'll probably have some notes, maybe not in part of this book, but what you can do about invariant maximality where the notions are multidimensional, the stuff I'm throwing away will still exist in some form in notes. And just that it won't be in this book. That's all I'm trying to say. All right. So almost identities are the big deal here. And these are the functions which are finitely different from a identity function. And we have one big theorem, the almost identity usability theorem, which gives a very simple, a quite simple very simple, I would say very simple, a sufficient condition for being usable. Sufficient. And we'll talk about that. Okay. And then it has there's a corollary, there's a corollary which has an alternative sufficient condition for usability. Now in this context, we reconstruct, we bring in the order theoretic functions. The order theoretic functions are already in that much earlier, that first section that's been around a long time. Order theoretic order theoretic sets are first order definable with parameters over Q less than. And order theoretic functions mean the graph is first order definable. Okay, order theoretic. And this is a very robust class. And the earlier chapter has characterizations of the order theoretic functions using elimination of quantifiers is the main tool to understand these. But we want to deal with it here. So we show that every strictly increasing order theoretic function is an almost identity. Not every order theoretic function is an almost identity because the constant functions are not almost identities, but the strictly increasing ones are. Then we talk about what's called completely regular. There's some very good almost identities, complete regular almost identities. And every almost identity can be extended to a complete almost identity. So, and the complete ones, when you complete it, the complete ones are order theoretic. And there are only countably many order theoretic functions. And these are very tangible. These are extremely tangible. More tangible even than famous things like piecewise linear, which are larger class. But there's continually many almost identities. There are continually many almost identities. So basically, this latter part is showing that the almost identities are superfluous, except for the ones that are very tangible. Only the very tangible ones mean anything, because the other ones are subsets. Yeah. So that's why the almost identity usability theorem is implicitly pi(0,1). That's why it's implicitly pi(0,1). Because it can be restated for order theoretic almost identities as equivalent. All right. But we keep our eye on the ball with one theorem. Remember, we're trying to lay this permanently into the mathematics community. All right. So this is not new. This is why the almost identity usability theorem is implicitly pi(0,1). Yeah, maybe I even should make the contents here a little bit different, but this is unchanged. And this uses Gödel's completeness theorem. This here. Okay, then we want to actually prove this AIU, and for the brackets K means K usable. AIU means it's always usable no matter what K is. And this is a triviality that we already handled because this is one usability. I actually prove this for 2 usability using omega-1. So the idea is the mathematicians can sort of understand that readily without having to be comfortable with large cardinals. And I do it along these lines here, but I didn't have time to embellish the table of contents here. I mean, I want to, not clear how I want to embellish the table of contents here. I think maybe I'll keep it this way. Well, that's a decision I have to make about whether elaborated in the table of contents, have another layer, or have more sections here, because I used to do that with the other ones. All right. So then we have it with dimension k, where it needs a k minus 2 subtle cardinal. And that's when k is greater or equal to 3, because we already handled these. And then the full one uses an SRP cardinal. An SRP cardinal is a little different terminology. It just means a cardinal, which is KSRP for every k simultaneously. All right. Then I apologize for wanting to get more detailed. For more detailed information, we'll just consider these simple these very simple cases of these very simple cases of embeddings of almost identities with very nice notation. When we get more detailed, it's convenient to just deal with these. So I make some excuse for that, so that I can give this this proof. Another reason you can just use omega 1, namely for this very specific almost identity. See, because then over here I'm not doing that. I'm actually only doing 2 usability. Here I'm doing full usability. So I didn't mean this, I mean this. This is confusing. So this is usable. Yeah, there's something that's usable. So the excuse for this is that we want to get, for some specific ones, we can actually get more refined information. Okay. And especially this refinement, because this is one where it's the gap between 0 and 1 over n that's allowing it to be provable at all. And the proof involves Erdős-Radu and the iterated exponentials on omega. The iterated exponentials on omega. And that's worth putting in, because that shows that, in fact, we don't just jump. See, right here, we just jump because AIU at 3 uses a subtle cardinal, a 1 subtle cardinal, that is. That's a huge jump. These are, by the way, none of this is reversed except this. None of this is reversed except this, the full one. So it looks like this is extremely, it jumps all the way from well below ZFC all the way to way above ZFC, but that's not quite the case when you get more refined about about the functions. Because when you do this, it's iterated exponentials. And I want to keep this material. It was rather intricate. And it's also true that when you oh, it isn't here. Here it is, 311. It's also true when the gap is at the end instead of in the front. And if I remember right, there's a soft there. I think I had or will have a soft derivation of 311 from 310, so it doesn't have to be redone. If I remember right, I'm pretty sure I should have that. One doesn't have to go examine the proof and modify it. I think one can actually get a soft derivation, soft equivalence between these two. Now, joint usability is very important, and I just have a little bit of this. One project is, since I completely analyzed what finite functions are usable, why don't I analyze what finite functions are jointly usable? Jointly usable means I can find a maximal chain that's embedded by all of these functions, not just one. And there's a very, there's an important lesson about this joint usability. When you have these very simple type functions, because that's all I've thought about, and it's much more complicated in general. So you have these simple ones are you have, I'm going to have to make up a name for them. Simple, maybe that's a good name. I don't know. It's the identity for a while starting at -1, and then it hops up in an arithmetic progression. So for example, the general case would be here with 0, except this is weaker with 0 here. So you can the same proofs show that if you have finitely many of these, in other words, the interval that's used is -1, 0 for the first one, like here. And then the next one is -1, 1, comma, 1 over n, the next one is -1, comma 2, and so forth. -1, 2, and with these things, and so forth. So when you have any finite number of these, actually infinitely many, but I don't want to go there particularly, although one can. But with finitely many of them, you wind up with the same result. That's usable. But the reversals are much easier. So this is worth mentioning, although in the book I'm not going to give easier reversals. However, and I don't want to do this in this book, with this extra massive power from having joint usability like that, the prospects of getting reversals, the prospects for getting reversals in fixed dimensions go way up. That may be the key to getting more refined information in the subject, going to joint usability and showing that in fact can be reversed or almost reversed at least. So that's an exciting prospect, but I definitely I'm not going to venture there in this book. After this book is something else. We can have an army of people trying to do stuff. So joint usability is a very rich topic, wide open, in any real generality. But there's some important things I already know about it. Formalization is just making honest, what do I mean by using a large cardinal or using omega 1, what does that mean formally? That this is all straightforward, been around forever in one form or another. Now, I do want a little section on graphs and emulators. I want the section on graphs because the reversal, if you remember, is a graph theoretic statement with clique, which is rather easily or trivially shown to be imply, all you need is one direction, imply, but even equivalent to the chain stuff. I just use chains all the time, but the cliques are, really like chains. A clique is nothing more than a chain in the edge relation, and the edge relation is a irreflexive symmetric relation. So I don't want to change this reversal. I'll claim that it's more convenient to work with graphs as the excuse, and then actually have this. Emulators are good because, and also the results, the idea is the results are all the same, easily modified, restated the main results for graphs and emulators without change. Though there is a little bit of an issue about dimensions. With emulators, you might need one more dimension. There's one dimension difference, maybe. I mean, certainly by what I do, but in theory, one has to actually see. But basically, emulators are important because that's the key to something that works for high school students, gifted high school. Emulators are a competitive way of doing things. Maximal emulators compared to maximal chains. So this is a soft chapter with nothing complicated in it. And then this is also quite soft with nothing complicated in it, showing that these statements that we're doing, that the AIU and even the corollary to AIU, which I think I wrote it as AIUE, even that corollary to AIU is independent, requires the larger cardinals, because it implies the statement being reversed. This is the slightly different notation for the new statement that that's reversed. Actually, the statement that's reversed is a little bit weaker than this. The statement being reversed, which is good. The statement being reversed has the dimension k the same as the number n. So 0 over k to k over k. So that's what's in here. And we can go through some details. The most of this I'm just going to I won't be talking much about until we get to the stuff, the really new stuff. The way I finally wanted, I spent a lot of time thinking how I want to organize this for the mathematician who's just, willing to think about this for 5 minutes only. So let's see. So we have this unchanged part of this is standard stuff about q comma less than. Standard stuff about q comma less than. And this is unchanged. This is unchanged. Just how you build maximal things and some of the computational complexity that come up. Now we get down to business about how I want to state this. Embedded maximality extends section 3.3 by requiring that the maximal chain has a given embedding. All right, so a partial function from A into B. So the double colon means partial function. This is an old notation we've done before. Okay, and then now here's the definition, which we've done before, of course. F embedded means it's a 1-1. I look up in the AI, what does the word embedded mean in mathematics? Everywhere it seems to mean that you require that it's 1-1. Now, actually, I am going to put a footnote in here. I mean, I'm going to make a side point in here that if I don't require it to be 1-1, that doesn't change the subject at all. That's worth mentioning. And that will be clear, that'll be clear from the final version of the text, okay? That I don't have to make it 1-1, but this is the way everybody does everything in math. It's called an embedding. It's required to be 1-1. So that for all things in the domain, the tuple is in the set if and only if the tuple is in the set when you forward image under F. And we say that F is an embedding of S. C means contained in. This means I didn't have time to format the lecture, that's all. Okay. So here is the statement that we are interested in. Here is the template. It's called OIR, order invariant relation, max, chain. F is the embedding, and -1, 1. This is the parameter. K is universally quantified. So every ordered invariant relation on every -1, 1K has an F embedded maximal chain. And a function is called usable if and only if this holds. And it's K usable if and only if this holds for fixed dimension K. Okay? So that's the setup of the subject, of embedded maximality. You start with this statement, this template, in which f is a parameter and k is universally quantified. All right, an observation. If f is contained in G and G is usable, then f is usable. Okay, and this turned out to be a very convenient, trivial observation. All right, now what is the most basic usability of all? The most basic is an easy consequence of the usual finite Ramsey theorem. So if f is a map, f is strictly increasing if and only if for every p less than q from the domain of f of p is less than f of q. The most basic theorem is that every strictly increasing finite function away from the endpoints is usable. In other words, entirely inside. This is almost completely trivially proved using the finite Ramsey theorem. Hence, I write ACA prime. For the argument that I didn't copy here, we really do need that 0 and 1 are not in the field in order to make the order preserving bijection. We can sharpen theorem 2411 as follows. Every strictly increasing finite map fixing the endpoints -1, 1 is usable because you use the finite Ramsey theorem with constants in there, which is not really different. So this is also very simple. So you have your foot in the door that certain finite maps are fine, just fine. Now let's divert ourselves to one usability, because this is full usability, all dimensions. So one usability, I'm sure we've been over this before. In the case of dimension one, there's really only 8 things good. There are only 8 relations on. There are only 8 relations on binary relations. Only 8 relations on q to the 1. I mean, excuse me, on -1, 1 to the 1. And here they are. The maximal chains are clear in each case what they are. They're either the singletons or they're -1, 1. And so from this, you can easily get that f is one usable if and only if either the field is missing a point or the function has a fixed point, one of the two. So you can easily prove this equivalence, as I do. All right, so one usability is really nothing. Two usability is deep. Now we have an old section about stability. It probably will have to be revamped a little bit. Obviously, I didn't format it completely here. This would be 5. Something like this, 4, 3, 1. Yeah, so this is stuff like that wasn't too nice. Let's fix that. Don't know why that's done that, but anyways. All right, let's not worry about this right now. All right, so this is stuff like isomorphism preserves usability, and it's preserved under composition, and empty set is usable, and all just nonsense, general nonsense all over the place. This is about reversing the order. I may change this because I don't think. Yeah, no, I use the minus function. Yeah, I do use this minus concept in the section on finite things. Yeah, I might have another way to say this also that I need to use. in a couple of places. Let's not to worry about this much. Okay, and everything has to be changed to embedding. That kind of thing. All right. So just some general nonsense about there's no notion of fully here that's an old thing. That's not relevant here. Okay, a lot of it here. All right, now this is not new. There isn't really any change. Yeah. Well, I already defined strictly increasing earlier. Probably I should have defined strictly regressive back when I did that. So there's some organization here. Okay, now if F is 2 usable, then F is strictly increasing. Now, if you recall, if F is 1 usable, there was essentially no condition. I mean, it certainly did not imply that it was strictly increasing, not at all. But so 2 usability is when things really get interesting. And this is an old thing unchanged. And this is also an old thing that's unchanged, although it's a little bit tricky. This means that if you, at the two ends, -1 and 1, if you go up here and you go up here to the 1, and down here you go from the 1 up, if the function does that, and I don't care what it does in the middle, it doesn't make a difference, that's enough to ruin usability. And that's been around for quite a while. And this is a triviality. And now we have the finite. All I did is copy the main findings. A finite function is fully usable, is usable. So now, this is not going to be usable means fully usable. Yeah. Finite function is usable if and only if every 2-element restriction is 2 usable. Right. Now let's get into the serious part. So the identity on E, and an almost identity means that it's IDE union G, where G is finite. Now, I actually now think that there's a slightly simpler definition I can give. A function is an almost identity if the set of non-fixed points is finite. I like that better. I should emphasize the convention that when you write not equals, both sides have to be defined. That's part of one of the main conventions of free logic. Free logic is something I adhere to. It's called free logic. And I adhere to it not just simply because it's free of charge. I don't have to pay for it. We all know we don't have to pay for free logic. All right. So the almost identities are the simplest general kind of infinite functions, in a way. Usability of almost identities is an unexpectedly deep matter. The almost identity usability theorem gives a simple sufficient condition for the usability of almost identities. We don't talk about degree here. That's another complication. Less is more. AIU is proved in section 3.9. I think it's 3.8, but who cares? Using an SRP cardinal. The existence of an SRP cardinal goes way beyond the usual axioms of mathematics. There's an alternative sufficient condition for the usability of the almost identities. We derive this alternative statement, AIUE, from AIU. The proof is elementary. In section 363, we show the strictly increasing order theoretic functions are almost identities. In 4, we show the strictly increasing almost identities extend to what we call regular completions, all of which are order theoretic. This allows us to use only regular completions instead of strictly increasing almost identities. All right, so some polishing of the wording of this will be made. But now we come to the almost identity usability theorem. A gap is a pair PQ such that P and Q are between -1 and 1. The field doesn't intersect PQ, so nothing goes on inside PQ. F maps -1P into -1P and Q1 into Q1. -1P into -1P and Q1 into Q1. Okay, I hope you can see the picture. P and Q are here, my two thumbs, and the function is really broken up into two totally independent parts, with nothing in between, so to speak. So I think that's pretty clear. So the almost identity usability theorem, AIU, says the following: every strictly increasing almost identity with a gap is usable. That's it. So that's the headline. Every strictly increasing almost identity with a gap is usable. Now, is every strictly increasing almost identity? Oh, by the way, strictly increasing, of course, is necessary. So we know that we need it. We know that we would have to have this in here. So the only concept that we're using is in this theorem is the concept of a gap, because the strictly increasing part is necessary by an elementary argument. Now, is every strictly increasing almost identity usable? Well, I'm not claiming this or refuting this in this book. I will say that I believe this is false, and I will give a sketch roughly of how you would take our existing complicated reversal and modify it and amplify on it in order to get that result. It may be that in order to show that there's a strictly increasing almost identity that's not usable, you're going to have to do something heavy like that. You're going to have to actually use the reversal plus another layer of another idea layered on top in order to do that. This is quite possible. I don't believe that every strictly increasing almost identity is usable. All right. And we prove this using a SRP cardinal, and we naturally calibrate. AIU of K. The star was, let's not get into why I put that in there, but it's gone. Every strictly increasing almost identity with a gap is K usable. And these restricted ones are also proved using lesser cardinals. Okay, now in this section, we derive a corollary, which is a very important one, called AIUE, that every strictly increasing almost identity fixing an endpoint is usable. When I say fixing an endpoint, there's only two endpoints, -1 and 1. So if you fix one of them, that's going to make you usable. So that's a very important corollary. All right. And so I proved that AIU implies AIUE. Now we go to the review of the order theoretic functions. The order theoretic functions are very robust. These are just the functions that are defined. Well, I define order theoretic to mean that it's defined by a propositional combination of inequalities with parameters. And there's a theorem that if S is contained, J always stands for a rational interval, which are required to be non-degenerate and have the endpoints the endpoints have to be extended rationals. So order theoretic means that you're definable. You're a propositional combination. That's what I'm trying to say. A propositional combination phi. This is formula phi. Why don't I just forget about that? Just say propositional combination of inequalities. Okay, and then this is stuff that's very well known to people in O minimality. It's completely standard stuff. Intersection of an order theoretic set with J, K. Okay, so all of this is all robust and all well-known stuff. It's equivalent to definability because of quantifier elimination. Now we only really need that discussion of order theoretic for subsets of the interval -1, 1. Okay, now we go through and show that for the purposes of proving AIU, we just have to worry about much more concrete, definite functions than just almost identities. Because every almost identity, strictly increasing almost identity, is contained in a very nice one. That's what we're going to show. Okay, and this definition, which may look a little artificial, is very helpful. A regular almost identity, strictly increasing, no isolated fixed point, and has a gap, the gap minus a half, a half. And the point is that you can take any almost identity and extend it to one of these. That's clear because you can kill the isolated fixed points by just making an identity on a little interval surrounding it. So there's no isolated fixed point at all. You can kill the isolated fixed points by making them a little bigger. They won't be isolated fixed points anymore. All right. I don't want to talk about degree of maybe I just want to stop there. Uh, uh, okay. What I want to say is the finite part, the finite part doesn't increase with no new elements in the finite part. That's what I want to say. Okay. And the realities that can also be uniquely decomposed as IDE union F, where F is finite. F will have no fixed points. F is called the finite part, and ID of E is called the identity part. There may be some cleanup to do here with this. All right, now this is the important theorem. This is non-trivial and interesting. Every rallid has a maximum rallid extension with the same finite part. Every rallid has a maximum rallid extension with the same finite part. This maximum rallid extension is order theoretic. So this means I can take, okay. Now every regular identity, almost identity, extends to a rallid. So you can do this. Okay, so the definition of a complete rallid is a rallid that no proper rallid extension with no proper extension, rallid extension with the same finite part. So you made it as big as possible, a complete rallid. Every strictly increasing almost identity extends to a complete rallid. I want to say something about the finite part here, but this isn't the right way to say it. All right. Exactly why I want to say that is for later chapters. I have to think that through. Okay, AIU and AIU K comma star are respectively equivalent if we restrict the strictly increasing almost identities with a gap to the complete rallid. So you can just state it in terms of complete rallids. That means that I just have to make my proof just based on the complete rallids. And here we do the structure of a complete rallid, and I'm going to finish up soon. So here is the complete rallid must have a left part and a right part, or a first part and a second part. The first part is on -1, 1, -1. Remember, minus a half, comma a half is a separation. Uh, what do I call it? Is a gap. We have a gap from minus a half to plus a half. So the first part is here, the first part is here, and the second part is here. And now the first part has exactly one of a bunch of forms. Basically, the general forms are, you might start with the identity map on an interval, followed by a finite function, followed by identity map, followed by a finite function, and so forth. But you may start with a function or an interval, or the identity function interval, or end with a function or identity function on the interval. Okay, and I'm saying that these functions are strictly increasing, and they're either strictly dominating or strictly regressive. You see, if you have a finite function and it's not all strictly dominating. Um, and has no fixed points, then there's got to be a gap. So there's some lemma in here about the existence of gaps in order to be able to know that you can put it in this form. And the other side similarly. And since these are complete, that means that, for example, you must start with -1 and end with, well, you must start with a half and end with 1. See. Okay, and our proof of AIU is made simpler by assuming that we have something of this form, but even a better form here. So if this is already good enough, we only have to look at the complete ralids of the form F1 less than the left part is F1 J1 dot 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 to Fn, where n is greater or equal to 2, n is greater or equal to 2. And G1, and the upper part, the second part is G1 through Gn. They begin and end with functions. So this allows one to give the proof in a much simpler way without, I mean, we're only talking about details, simplification of details. We're not talking about really serious ideas. So there's only one serious idea needed. There's only one group of serious ideas needed to prove these things from large kernels. The format of exactly how this is set up is relatively minor, but it still has to be done right and totally understandable. And that's what this is about. So usability is implicitly pi 0, 1. I think perhaps this was done. Oh yeah. This is old stuff, except it's adapted. This part is adapted. This is general and been around for a long time. And then the proof of AIU, I'm not going to talk much about here because I'm running out of time. But basically, we start with something like this, and this one's trivial. And I stopped here for even explaining what I'm going to do. But basically, it's the same thing that we've been doing. We go to the transfinite. We have an ordering that's obviously lifted from the rationals, from the original problem. And then we're in the transfinite. We use this thing called kappa cross the rationals from 0, 1 left closed. So we make ourselves dense. We have that ordering, but then we have another ordering, which is a well ordering, which is the well ordering, and that's delicate. Before we did that, we were calling it less than double star. We do a similar thing here, except that ordering, which is the order in which the transfinite recursion is conducted to create the inductive chain, which is maximal, but better than maximal. To create the inductive chain, we have to do a transfinite recursion. The question is, what is the order in which we do things? In other words, what is the well order that we're doing the transfinite recursion on when we build the inductive chain? And that depends delicately on this data. That's why I wanted to put it in reasonably simple form with one case only. All right. Now, when I want to get more refined information, I may well have to consider more cases than this. So I haven't quite worked out expositionally how far I can go, but to prove the main result, just the AIU, almost identity usability theorem, I do just need that it has this form, starts and ends with the functions. All right. So I think I'm done here. Andreas, this